suppose f of x is defined and continuous on the closed interval AB, then the region R above the x-axis, bounded by the graph of y equals f of x, and the line x equals a and x equals b, has an area given by the integral of f of x dx from a to b.
Now, when we say that a function is defined on an interval, or let's say defined on a set, so for this case, the function is defined on AB, then it means that the function value always exists for all x's in the interval AB. And when we say that f of x is greater than 0, it means the function value is always positive on AB. And if a function is continuous, it means that when you sketch the graph of the function, you would not be lifting your pen from x equals a to x equals b. So that's what it means. Now let's look at it graphically.
It said that the region has to be above the x-axis. Now suppose this is a graph of our f, where we can say that this is y equals f of x. The region is bounded by y equals f of x, the line y equal to 0 or the x-axis. From the left, it is bounded by x equals to a, and from the right, it is bounded by x equals b. Hence, we get our region R described by the theorem above.
Now, if only our region was a rectangle, then things would have been very easy for us because we would simply be getting the product of the length and the width. Unfortunately, our region is not a rectangle. It's an irregular shaped region, so we'll have to find other ways. Now, one way to do that is to divide the region into subregions that would somehow look like rectangles. So we'll have to divide AB into n sub-intervals. Okay, so let's look at it this way. Let this line represent our interval AB with the left endpoint A representing x sub O and the right endpoint B representing x sub n. In between them are the endpoints of our subintervals x sub 1, x sub 2 up to x sub n. Okay, so this means that our interval AB is represented or can be represented as a union of the sub-intervals from x sub interval x sub O, x sub 1 until interval x sub n minus 1 up to x sub n. Okay, so let's examine each interval. The length of each interval will just be computed as the difference between the endpoints. So x sub 1 minus x sub O for the first, x sub 2 minus x sub 1 for the second, and for the last interval, x sub n minus x sub 1. This means that for the ith subinterval, the distance or the length of the ith subinterval is just x sub I minus x sub I minus 1. So let our delta sub I of x represent the length of the ith subinterval, and let's locate them on the x-axis. So you can just put them randomly there, and then we try to locate where the ith subinterval is. Okay, here. Now on the ith subinterval, we can pick a random point between x sub I and x sub I minus 1, and we can name this x sub I star. Okay, then we locate this on the graph, meaning its corresponding point on the graph. If you notice, this point on the graph has a coordinate x sub I star and f of x sub I star. You'll notice that we will be able to produce a rectangular strip that spans the ith interval. Okay, so we will be doing this to every subinterval. That is, we'll have to locate x sub 1 star, x sub 2 star, until x sub n star. And we will also be producing rectangular strips for every subinterval. Okay, so these are the rectangular strips. So see if you connect them. There. You're producing rectangular strips. Okay, we have to take note that these subintervals don't have a uniform length. But we can make the length uniform or equal for each subinterval. So we say that without loss of generality, that the length of delta sub I of x is equal to b minus a over n. So that would be the uniform length of all the subintervals. Then it implies that the ith rectangle will have an area that's equal to a uniform area, which is equal to length times width. So the length is the height of the rectangular strips, which is f of x sub I star, and then the width is the length of the interval, which is delta sub I of x. Okay, so now let's take the sum of the areas of the rectangle, because we would take the sum of the areas of the rectangular strip to be the estimate to the area of the region. So we can denote this as A sub r, or we can denote it as dA. In sigma notation, we can, or in sigma notation, this is equal to the summation of a sub r sub I ranges from 1 to n. Now, if we observe closely each of our rectangular strips, there are a little part of the rectangular strip that is beyond the region, and then there are also some areas of the region that is not included in the rectangular strip. So beyond the region, that's an overestimate, and below the region, not inside the rectangular strip, is an underestimate. Okay, so each of our rectangular strips has an over and an underestimate. Now, if we try to increase the number of rectangles or the number of rectangular strips, what do you think will happen? We'll observe that the more rectangular strips we have, the narrower our rectangles will be, or the width of our rectangles. So if we have narrow rectangles, it would imply that there will be lesser, or we will be able to minimize the number of over and underestimates. So if you observe, let's look at this. The areas beyond the rectangles that are under the curve gets minimized. Okay, so let's write it down. Remember that our n represent the number of subintervals, so that would also represent the number of rectangles, right? So if we increase our number of rectangles, it means we're increasing our n. So increasing our n infinitely would imply an infinite number of subintervals. Having an infinite number of subintervals would imply that the width of each of our rectangular strips would get narrower and narrower as n increases. Okay? So, in symbols, as we let n approach infinity, our delta sub I of x would approach 0, right? Because as n increases, the length of the subinterval gets narrower and narrower, meaning it gets closer and closer to 0. So, this would imply a decrease in the number of over and underestimates. Which means that the limit of the sum of the area of the rectangular strips would be equal to the area of the region as n approaches infinity. So let's write it down. A sub big R, or the area of the region, is equal to the limit of a sub small r as n approaches infinity. And this is equal to the limit of the summation of our a sub r sub I, or the area of the rectangular strips, where I ranges from 1 to n as n approaches infinity. In terms of length times width, we can say that a sub big R, or the area of the region, is equal to the limit as n approaches infinity of the summation of I from 1 to n of the length times the width of each of the rectangular strips. So that would be f of x sub I star times delta sub I of x. Now, when we have the limit of the summation, we can have it represented by the integral, and then our f of x sub I star would be f of x, and our delta sub I of x would be our delta x. And since the bounds of our x is from a to b, x equals a to x equals b, then we have the bounds of our integral. So we have the area of the region is equal to the integral from a to b of f of x dx. So here we have the formula.